After knowing that the running time of an algorithm depends on the problem input size, the next issue concerns the unit that must be used to measure the running time. Can we consider the execution time in seconds or milliseconds as the unit for the running time? I mean, after the algorithm is designed and implemented by a programming language, run it on a computer for a certain input and measure the execution time. If it takes little time to execute, conclude that the program is fast and efficient. Otherwise, conclude that it is slow and inefficient. Of course, using the execution time as a unit for measuring the running time of programs is not reliable and has drawbacks. Because when you run a program on a computer, the execution time is affected by some factors that make the actual readings of the execution time incorrect. So what are these factors that affect the execution time of programs? The first factor is computer speed. I mean, when you run a program on a computer, if it takes long time to execute, you cannot be certain that it is slow. Because when you run it on a faster computer, it will be fast. And if it takes short time to execute, also you cannot be certain that it is fast. Because if you run it on a slower computer, it will be slow. The other factor is the quality of a program implementation of the algorithm. The way an algorithm is implemented can significantly affect its running time. For example, a poorly optimized code can lead to longer execution times even if the underlying algorithm is efficient. Factors such as inefficient data structures, unnecessary computations, or lack of parallel processing can all contribute to increased execution time. Execution time also depends on the compiler generating the machine code. Different compilers may employ different strategies for generating machine code that can lead to significant differences in performance and running time, even for the same source code. A compiler might have advanced support for specific data structures or algorithms, allowing it to generate more efficient code for those constructs. When trying to clock the actual running time, various factors can introduce inconsistencies in the results. For instance, if the CPU is busy with the processes running in the background, the execution time of the program can increase, making it difficult to get the correct clocking for the running time. In summary, while time can provide some insights into algorithms' performance, it is not a reliable unit of measure that can be used to find the time efficiency of the algorithms. The solution is to have a metric measure that does not depend on any of the above-mentioned extraneous factors. This metric measure is the number of steps the algorithm takes to execute its operations. In general, the running time of an algorithm increases with the size of the input. And also the running time is roughly proportional to how many times the algorithm's operations, like comparison, are executed. So to find this metric measure, we analyze the algorithm by determining the number of times each operation is executed as a function of the size of the input. We will have two types of analysis. First is the detailed analysis. The second is the quick analysis. In the detailed analysis, we count the number of times each of the algorithm's operation is executed. As you will see later by an example that it is difficult for some algorithms and unnecessary. For the quick analysis, first we identify the most important operation that is called the basic operation, and this operation contributing the most to the total running time. Then we count how many times this basic operation is executed. For most of the algorithms, the basic operation can be found in the innermost loop of the algorithm. Our next discussion is how to identify and find the basic operation of an algorithm. The basic operation is the operation that contributes the most towards the running time of the algorithm. In other words, if the algorithm is spending most of its time executing an operation, then this operation is the basic operation of the algorithm. So what is the guideline that we need to follow? to locate exactly where is the basic operation in the algorithm. To determine the basic operation, you need to follow two steps. The first step is to locate the statement or line number in the algorithm that contributes the most towards the running time of the algorithm. If your algorithm consists of nested loops, then select one of the statements in the algorithm's innermost loop. After locating the statement that contributes the most towards the running time of the algorithm, this statement may consist of more than one operation. Select the most time-consuming operation in this statement using the following order from highest to lowest execution time. The division operation is the most time-consuming operation among all other operations in the algorithm, because the hardware or the CPU implements a very complex algorithm that takes a lot of execution cycles to divide two numbers, especially division of floating point numbers. But division by a power of 2 is treated differently. In fact, division by a power of 2 takes fewer execution cycles because the hardware implements it by shifting bits to the right. For example, dividing a number by 2 is implemented by shifting the number 1 bit to the right, dropping off the rightmost digit. And dividing by 4 is implemented by shifting the number 2 bits to the right, dropping off 2 bits. And so on for division by 8, 16, 32, 64, any number power of 2. Examples of the division operation is when you divide a over 6 and 6 is not a power of 2, dividing a number by 9 and 9 is not a power of 2, dividing a over b assuming b does not have a value that is power of 2, and so on. The next operation is the multiplication operation, but not by a power of 2. Because multiplying a number by 2 is implemented by shifting the number 1 bit to the left, inserting 0 in the rightmost digit. And shifting 1 bit takes fewer execution cycles than multiplying by 2. Examples is multiplying by 5, which is not a power of 2, multiplying two numbers a and b and it is assumed that none of them is equal to a power of 2, and multiplying 5 by 3 and none of these numbers is a power of 2. Next will be the addition, subtraction, increment and decrement operations. All these operations are at the same level. Examples b plus c, a plus 1, n minus 4, and so on. Next will be the comparison operations. An example is comparing n if it is greater than or equal to 0, comparing a if it is equal to 7, and comparing b if it is less than a. Next is the division and multiplication by a power of 2. These operations are implemented by shifting 1 bit to the right for division by 2 and shifting 1 bit to the left for multiplying by 2. Examples: dividing n over 2, or multiplying n by 16 and 16 is a power of 2, or dividing n by 32 and 32 is a power of 2. The hardware implements these operations by shifting 1 bit left for divide by 2 and shifting 1 bit right for multiplying by 2. They take fewer execution cycles than division and multiplication. Finally is the assignment and return statements. Examples: assigning 0 to a, returning a, assigning b to a, and etc. So this is the order of execution of operations, from the most time-consuming operation, the division, to the lowest time-consuming operation, the assignment or the return operations. As a final remark, if we have a toy or dummy algorithm, I mean a piece of code that consists of some selections or loops that is not designed to solve a certain problem, then we can blindly follow the guideline presented here on this slide and select the most time-consuming operation wherever it is in the algorithm. However, if the algorithm is a solution to a certain problem, such as the problem of finding the maximum element in an array, or the problem of multiplying two large numbers, then the most time-consuming operation will be an operation that is related to what the algorithm is doing. For the example of finding the maximum element, the algorithm is spending most of its time comparing the array elements to find the maximum element. In this case, the comparison operation will be certainly the basic operation of the algorithm. Also, for the example of multiplying two large numbers, the algorithm is spending most of its time multiplying the two numbers digit by digit. As a result, the multiplication operation will be most probably the basic operation of this algorithm. Let us have a look into some popular and important algorithms and find out what are their input sizes as well as their basic operations. We will present examples of input size and basic operation of some of the important problem types. The input size, as we defined it before, is a numerical parameter related to the problem type that affects the running time of the algorithm. The basic operation is defined as the operation that contributes the most towards the running time of the algorithm. In this table, we list some of the problems with their input size as well as their basic operations. The first problem is the searching for a key in a list of n items problem. The input size will be the number of list items, n as a parameter. The basic operation is the key comparison, because for searching for a key, the algorithm will spend time comparing elements to find the key. The next problem is the multiplication of two matrices problem. The input size is the matrix dimensions or total number of elements of these dimensions, or total number of elements of these matrices, or total number of elements in these matrices. The basic operation is the multiplication of two numbers. The next problem is the problem to check whether a given integer n is a prime or not. The input size will be the size of the input parameter n, number of digits in binary representation. The basic operation is the division operation. Finally, for typical graph problems, the input size measure will be the number of vertices and/or number of edges. The basic operation is visiting a vertex or traversing for an edge. Our next discussion is how to do detailed and quick analysis on some of the algorithms.